So the next talk is by Xuhua He from the Chinese University of Hong Kong, and it's the second part about flag manifolds over semifields.
Okay, so thank Daniel for the introduction, and it's actually my pleasure to give a talk here. And well, I have to say that actually I'm sorry that actually I could not actually join most of the activities for this special year as I actually had planned to do in the beginning, but and now actually the traveling is actually is really a big problem. So what I'm going to do is that this is the second part of the talk on the flag manifolds over semifield. Huan Chen actually gave a talk on the first part. So he actually focused on the flag varieties of any Kasmuti group over semifield. And so what I'm going to do today is that, for today is that we are not consider arbitrary semifield, but we are just focus on the semifield, which is the positive real numbers. And so, this actually goes back to Lustig's 1994 paper, the theory of the total positivity. And so today we're going to focus on the flag and the partial flag, the totally non-negative part of the flag variety and the partial flag variety, but for arbitrary Kasmuti groups. So the thing which we are going to focus on, we're going to discuss some nice geometrical properties of the totally non-negative part of the flag varieties. And so this actually is established using some deep representation theoretical and geometrical topological results. And so I would say that actually it's probably in some sense different from most of the talks in this workshop, is that the geometry is used to study some representation theoretical problems. And so what we're going to do here, in some sense, is the other direction. We're going to use a representation and theory and to obtain some nice geometrical results. So in the beginning, I'm going to recall the definitions of the totally non-negative part of the flag variety, in case some of you did not attend the Tuesday's talk or did not remember the details. Okay, so we want to start Kasmuti group, which we call G, and to be specific, we're going to use this so-called the minimum Kasmuti group. So we actually fix the pinning. We have this is the torus T, and we have the two opposite barriers, B plus and B minus, and we have a set of the simple real root subgroups Xi and Yi. And a particular example is that we can think about the G just a GON, and then T just a diagonal matrices, and the B plus minus are just upper triangular and lower triangular matrices. And so we have this Xi just many the diagonal with only A above the diagonal, and Yi with only one A below the diagonal. And so we start from this pinning, then we can actually define this is a totally non-negative part of the uniform radical U plus and U minus. So here the U plus totally non-negative is a submonoid of G generated by XIA. I runs over all the simple roots, and A are just all the positive real numbers. And similarly, if you change the plus to minus, the U minus, totally non-negative, this is a monoid generated by YIN. And well, so although we are in the Kasmudi setting, but this result actually follows exactly this, as Lustig did in the 94 paper for the reductive groups, is that the totally non-negative part of the U is a disjoint unions of the cells and indexed by the Y group. And so as you know, this actually cells to be the U plus and minus W positive. Okay, so how do you actually define the the totally non-negative flag varieties? Well, so one thing I would like to point out is that actually we actually have to be a bit careful when we talk about the flag varieties for the Kasmudi group. Because we know that for arbitrary Kasmudi group, the two barriers B plus and B minus, they do not conjugate. So here we want to be specific that we just use a B plus. So we take the G quotient by B plus, and this is our full flag variety. Okay, so well, how to define the totally non-negative flag variety? Well, so in the case where G is a reductive group, this actually first introduced by Lustig in the 94 paper. And he actually has the first and the second definition, and then later on, Marsh and Rich in the 2004 gave the parameterizations of the decomposition of this totally non-negative part, and which we can also use this as a definition. And for arbitrary Kasmudi groups, and so this is obtained in a joint work with Quentin Bao, and based on the a series of the works of Lustig recently. Okay, so anyway, so how to actually define the totally non-negative part of the flag variety? Well, so we actually have the several different ways. They are all equivalent. Well, first of all, we actually have this which I call this the topological definition. Is that well, we have defined this as a monoid, the totally non-negative part of the U minus. And so this we actually acts on this B plus. And then we take this closure inside the flag variety with respect to the Hausdorff topology. And there's another which is totally different definition, which actually using the canonical basis. Is that we start with a dominant regular weight, and then we actually look at all the projective lines in this V lambda, and then we actually then we have the natural embedding of the flag variety into this one, and so we actually just consider the intersection of the flag variety with the totally non-negative part of this projective space. So this actually the totally non-negative part is just we actually consider the non-negative linear combinations of the canonical basis. And well, there's another way. Well, you may actually either think about this actually as a definition or as the property. Is that well, I'm not going to the details of this, but there's a so-called the map introduced by Marsh and Rich, which for each pair V and W V less than equal to W in the while group, and they define a particular cell inside the flag variety, and then we actually take this the disjoint union together. And so, so the result we actually have is that all these three definitions coincide. Let me actually say a few more words about the third one, because we are going to actually use this actually quite a lot in this talk. If you actually think about the flag variety over any field, so we have the decomposition of the flag varieties into the disjoint unions of the Schubert cells, B plus, WB plus. And also we have a decomposition of the flag variety as the disjoint unions of the opposite Schubert cells, the B minus V axiom B plus. So the open Richardson variety is defined as the intersection of the Schubert cell with the opposite Schubert cell. And where it's actually proved by Castaner-Lustig is that this intersection is non-empty if and only if V is less than or equal to W. And in this case, this is the open Richardson variety, is an irreducible variety, and the dimension is a length of W minus length of V. So I would like to point out that when we talk about the total positivity, we do not use the Zariski topology, but instead we use the Hausdorff topology. And if you actually look at this actually over R, and in the Hausdorff topology, this is not connected. And it's actually proved by Connie Rich that this is the BVW positive. This is a totally non-negative part of this open Richardson variety. This one is a connected component of this open Richardson variety over the real numbers. And so I would like to mention this example, which is actually also mentioned by Huan Chen and in the talk on Tuesday. However, I would like to recall this. So if you actually look at this, actually the GSO2, then the flag variety is just P1. And the totally non-negative part of the flag variety, so it consists of this I do this by three parts, 0 and positive numbers and infinity. Okay, so how do we actually see the cells? So we actually have the three Richardson varieties. And so 0 corresponds to this V and W both equal to 1. And infinity corresponds to this actually both equal to S. And this open part and the set of the positive real numbers is a one-dimensional cell corresponds to the pair 1 and S. So these are all the choices of the V less than or equal to W for the group SO2. And so I'm not going to give you the precise definition of the Marsh-Rich map, but I'm going to actually say what happens in this particular example. So here this actually this is a B11, so we just only have this is a B plus, and so here this is BSS. Then we just have this S dot with axiom B plus, and here this is actually 1 and S. So here we just use this YA, and with a positive. So this actually gives you the one-dimensional cell. And it's also interesting to say, okay, what actually happens actually if you actually think about all these things together. And well, you can see this actually this is a closed interval, but I would like to mention that actually, in fact, we can also think about this as a one-dimensional closed form. And in fact, this will be true in the general case. Okay, so well, this is actually what happens for the full flag case. So for the partial flag, and so what we're going to do with a partial flag. So for the partial flag, we start with a set of the we start with a subset of the simple roots J, and then we denote it by Pj plus the corresponding standard parabolic subgroup. And then we actually have this Pj, just the G quotient by this the Pj plus. So this is what we call this the partial flag. And there are actually many important examples that actually worth to consider. For example, the Grassmannian or the Avant-Grassmannian, and there are many others. So how do we, any questions? Well, how do we define the totally non-negative part of the partial flag? Well, there are actually several ways to do this. One way is that we start with the totally non-negative part of the full flag. And then we consider about this projection map from the full flag B goes to this partial flag. And then we look at its image. And another way is that we can actually follow the similar definition as we did here. So in the full flag case, we have this topological definition. We actually take the closures of the U minus totally non-negative orbit. So this definition remains valid. So we can actually also have this topological definition. We take this closures of the U minus totally non-negative orbit on Pj plus with respect to the Hausdorff topology. So if you actually look at this representation theoretical definition, well, unfortunately, we actually still do not know. We still do not know actually what happens for the partial flag.
No, it's true. That's not true. There is a definition.
Oh, well, sorry. Yes, you are right. There is a definition. How do I say that? Well, there is a definition, but we do not know whether or not this actually coincides with the others in the general case. You have the conjecture back to the 90s, and which is still open in the general case, right?
No, but in a finite case, it coincides with all the other definitions.
Okay. Thanks for pointing this out.
Yeah.
Okay, I'm probably going to ask you later about this. Thanks. In the Katsumudi. Okay, and so and well, the other part is that have this algebraic or combinatorial description using this actually as this cells using the March-Rich map. And well, I would say that actually this actually is still true, but actually under non-trivial modification. So we're going to replace the open Richardson variety in the full flag by the so-called the projective Richardson varieties in the partial flag. And well, so this part is actually is a bit technical. So I'm not going to mention it right now, but we're going to discuss it later. Okay, so another thing I want to mention is that in the finite case, there is indeed a duality. Well, so as I mentioned, in the finite case, we have this two Fourier subgroups, B plus and B minus, and they are conjugate. And so they actually lie, they both lie in the flag variety. And then we if we want to define the total non-negative part, so in fact, we can define the total positive part of the flag, which is the U minus strictly positive, axiom B plus, and this is the same as the strictly positive part of the U plus axiom B minus. And if you actually take the closure, if you actually take the closure, then they actually coincide. So in the finite case, so here instead of thinking of, we can actually change, you can also change the sign, change also this to the U plus axiom PJ minus, but this is actually only true for the finite case. And later on, we're going to say that this actually indeed actually cause a lot of trouble and makes the things much more difficult to handle in the Kac-Moody case. Okay, any other questions for the definition? Let me see some comment in the chat. Okay. Okay, so the goal for today's talk is that we're going to discuss the following. We're going to actually try to see the geometrical properties of the cells and these closures in the totally non-negative partial flag varieties. And well, so what we would like to know is that this is the decomposition of this is a partial flag into those cells. They form the so-called regular CW complex. So what this actually means exactly, well, it actually has two parts. The first part is that the closure of each cell is the unions of the other cells. And the second is that the closure of each cell is homomorphic to a closable. And well, let me actually mention a bit about history or motivations. That's actually why we are interested in and to understand actually such properties of the total non-negative flag variety. And well, actually, they actually from, well, we can actually think about this actually either from the Lie theory or from the poset topology. Well, from the Lie theory, so in the 1904 paper, when Lucic introduced the total non-negative part of the partial flag, well, he mentioned that actually this one is a remarkable polyhedron subspace. So one would actually expect that this actually has really nice geometric and topological properties. Well, another motivation is actually it's related to old problem which asked by Bajorner in 84. So he asked which poset, which partial order set can be reasonably interpreted as a phase poset of a regular CW complex. And in the 2000, Fabi and Shapiro, and they actually conjecture that certain subsets from the total productivity would give the regular CW complex. And so the thing which actually we related to this actually particular the partial flag is actually is due to Posnikov. Well, who actually conjectured this actually for the Grassmannian, and the later Williams generalized this actually to arbitrary partial flag and for the reductive groups. So well, their conjecture was proved very recently and in a series of papers by Galashin, Kaplan, Line. Well, they actually first proved that the full flag and then partial flag, and then each cells are homomorphic to a closed ball. So in this series of papers, they actually showed that this is the serial decompositions of the totally non-negative part of the partial flag for reductive groups form a regular CW complex. So in a work in progress with Huanchen Bao, well, we are going to extend this result, the result of the Galashin Kaplan line to the Katsumuti groups. But here, well, there are some technical issues, and we need to make this assumption that the WJ is finite. Okay, then we say that actually if G is a minimum Katsumuti group, if we assume that the W lower J is finite, and then the totally non-negative part of the partial flag variety is a regular CW complex. Well, I would say that actually there actually some part of our approach actually is actually very similar to the Galashin Kaplan line, but there are several difficulties which actually mainly due to the Katsumuti groups, and also actually say that they actually do have some which leads to some interesting mathematics. So so in the remaining half of the time, so I'm going to actually go into some part of the proof. I'm going to explain some ideas which actually say how do we actually understand the geometrical and topological properties of the serial decompositions of this totally non-negative part of the partial flag, and also some and also actually some of the steps which actually really actually depends on the deep result from the theory of the canonical basis. Okay. Let's actually first actually goes back to the statement. What do we want? Well, we actually have the two parts. Well, first we want to actually understand that the closure of each cell is a union of the other cells. And second, we want to show geometrically how the closure of each cell looks like. Okay, so let's actually first try to understand about the closure relation. And well, the closure relation, and so if you actually start with a cell which is actually indexed by V and W, we take the totally non-negative part of it, take its closure, then the closure relation is actually easy to describe. We just have this another pair, V prime and W prime, and the condition is that V prime and W prime lies between V and W. Well, I would say that actually this result is not surprising, and because if you actually think, if you forget about the total positivity, if you work consider what happens over fields, then this actually BVW, this open Washington variety, is the transversal intersection of a B plus orbit with a B minus orbit. I mean, here the B plus and the B minus actually the orbit intersecting transversally, and well, because it's a transversal intersection, and then we know that actually the closure of the intersection is equal to the intersection of the closure, and this is actually how we actually get this result immediately. However, if you don't work over field, but instead over the positive real numbers, then if you look at this one, then this one is not an algebraic variety anymore. It is actually it's a semi-algebraic set. So to study the closure of the semi-algebraic set is much more difficult. So I would like to also mention what happens in the case where G is reductive, and then this closure relation is actually is known, and actually is actually proved by Connie Rich in the 2006. And here the crucial part of her approach is actually based on the duality. We actually have this is a B plus and the B minus duality. And so in particular, we have this is a U plus. So let me write it down. So we actually have this is a U plus. So well, once we actually have this duality, then this actually makes a lot of the argument actually much easier to understand. And but I mean, unfortunately, for arbitrary Kac-Moody group, we don't have this duality. So we need a new approach in order to understand about this closure relation. Well, so what we're going to do is the following. So we know that actually this the fourth flag also has a canonical open covering. This open covering is indexed by the wire group elements. Is that well each well, we know that actually the B minus axion B plus, this is actually open. So then we just shift this by the different wire group elements. And so what we're going to do is that we actually use this the positivity properties of the canonical basis. And so this and also we actually use the definitions of the totally non-negative part of the flag variety, and using this as the canonical basis. And then we actually show that this cell, so this cell is actually contained in any of the open part of the flag variety once we actually have this actually U lies between V and W. And well, why we are interested in this is actually because that we have a nice decomposition. And so if you actually look at this this open part, so we know this actually isomorphic to the U plus. And so U plus is the unipotent group, and we have the nitro decomposition. I think the U plus intersection with this the U inverse axion U plus and U inverse axion U minus. So we actually have this this isomorphism. And if you actually goes back, so this actually gives you an isomorphism from this open part of the flag variety to one Schubert cell times one opposite Schubert cell. And well, what we're going to show is that, in fact, this decomposition is compatible with the total positivity. So we actually we have this decomposition of this larger cell, the BVW, straight positive, which is as a product of this the BVU and the BUW, and both actually take the total positive. I have to point out that actually this actually is not an arbitrary decomposition, because we actually know this one is a cell and this actually two are cells, and actually to know that they are homomorphic, we just check that they have the correct dimension. So here the key point is that this homomorphism comes from this isomorphism. So in other words, if you let the V and W varies, and then we can actually take the unions of the several different cells from the left-hand side, and then we have the corresponding decomposition on the right-hand side. And this actually is very useful to understand about the Chlorine relations. So because actually we have this U lies between V and W, so presumably these two will be actually have the smaller dimension, and the Chlorine relation are understood. And so once we actually have this compatible homomorphisms of the various of the cells, then once we know the Chlorine relation on the right-hand side, this actually would gives us a lot of information on the Chlorine relation on the left-hand side. And by putting all these informations together, so we are able to prove the Chlorine relations. Okay, so this actually, roughly speaking, how we actually understand about the Chlorine relation. And now let me actually describe what actually happens in the case of the full flag variety, and how do we actually know that the Chlorine of each cell is homomorphic to a closed ball. And so here we are mainly follows the ideas of the Galashin, Karp, and Lime. And the first step is that we have this decomposition. So by looking actually in the details of this decomposition, what we can show in fact is that the Chlorine of each cell is in fact a topological manifold, and with this boundary which is just given by the other cells. And so if we argue by the induction, then we know that actually for all the other cells, this actually the Chlorine actually are the Chlorines are homomorphic to a closed ball of the smaller dimension. And also there's some nice combinatorial property which actually controls roughly how these actually different cells they are glued together. By putting these informations together, and then we know that actually the boundary is homomorphic to a sphere. And in the final part, we have to use this generalized Poincare conjecture, which actually proved by Smell for the dimension larger than 4, Friedman for dimension 4, and then Paraman finally for the dimension 3, is that if you actually start with any compact, contractible, n-dimensional topological manifold, and whose boundary is homomorphic to the n-1 dimensional sphere, then this topological manifold is homomorphic to an n-dimensional closed ball. So this actually, by putting all these actually informations together, then we actually know that actually the closure of each cells in the totally non-lit part of the flag variety is homomorphic to a closed ball. Okay, any questions? Now let me actually explain what actually happens in the partial flag case. We first actually want to actually discuss about this generalizations of the Wilson variety. How to actually think about this decompositions of the partial flag variety? A naive way is that we look at the decomposition of the partial flag into the Schubert varieties, which are just the B plus orbit, and also the opposite Schubert cells, which are just the B minus orbits, just a B plus orbits, and opposite just a B minus orbits. So, both the B plus orbit and the B minus orbits, they are indexed by this W upper J. This is a set of the minimum length representatives in this quotient, W quotient by W lower J. And so similarly to the partial flag case, we may actually define the Wilson variety as the intersection of the Schubert cell with the opposite Schubert cell. However, the Wilson variety in the partial flag variety, they actually, in some sense, they actually are not well behaved. So, what we actually usually consider is actually the so-called projective Wilson variety. And if you actually look at the definition, and it's actually a bit more complicated. And I'm not going to actually give you the precise definition, but I would like to actually tell you the index set. So, here the index set, it consists of the pairs V and W. Well, W lies in this W upper J. But actually the V, we do not actually assume that V lies in the W upper J. So we only assume that the V is an element in the wire group. And here still we want the V to be less than or equal to W. And so this one actually gives you a refinement of the Wilson varieties of the partial flag. So let me actually give you one example so you can actually get some sense that there's some difference between the open Wilson and the projective Wilson. And so open Wilson actually are indexed by a pairs of the elements in the W upper J, which actually satisfy the Bourgeois order. So we actually have 1, 2, 3, 4, 5, 6. We have six of them. And the projective which are then actually indexed by this is the Q lower J. So if you actually list them, we actually have 7 of them. So we have the exact 6, the same as above. However, because of the first one, we actually can take this to be in the W lower J. So we could actually also have this is a S2 and S2 S1. So in fact, this one. So the open Wilson variety in the partial flag indexed by 1, S2, S1, decomposes as the unions of these two projective Wilsons. So if you write this actually explicitly, so this 1, S2, S1 is the two-dimensional, just corresponds to these lines, A1, A2, A3. Sorry, there's a typo. So here the condition that A1 and A3 are non-zero. And here, this is a projective Wilson variety. 1, S2, S1 just correspond to that. Well, we still want A1, A3 to be non-zero, but also we want this A2 to be non-zero. And so this actually gives you something which is actually two-dimensional. And the other is that S2, S1 is that we want A1, A3 to be non-zero and A2 to be zero. And well, there actually is different reasons that actually why the projective Wilson variety actually behaves better than the Wilson variety. And so here I just want to mention what happens if you think about the theory of the total positivity, is that instead of thinking about all the real numbers and non-zero real numbers, we just think about the non-negative real numbers and the positive real numbers. And then in this case, if they're all positive, then this actually gives you a two-dimensional cell. And here we have A2 to be zero, and A1, A3 to be positive. This gives you the one-dimensional cell. However, if you only impose this condition that A1, A3 are positive, we don't do anything for this A2, then this one, the totally non-negative part of this is not a cell. So this is the reason that actually we actually need to find a refinement of the Wilson variety. So in order to actually to understand this geometrical properties. Well, another reason that why we actually we are more interested in the projective Wilson variety than the open Wilson variety, is that if you actually look at this projection map from the full flag to the partial flag, and if you actually take the any closure of the open Wilson variety in the full flag and look at its image, then the image in general cannot be what are the unions of the Wilson variety, but the image is always a unions of the projective Wilson varieties. And we actually do have an explicit formula for the right-hand side. And so, well, because this pi is proper, since we actually know exactly the Chlorine relation on the left-hand side, and also for the totally positive part of the left-hand side, and so we can see actually the Chlorine relations on this index at Qj is in some sense, this is a folded versions of the Bourgeois order on the W times W. What do I mean this actually folded? So this actually precisely the descriptions of this partial order. So if you have this V and W, we have these two pairs like in Qj. We see one is actually less than the other with respect to this Chlorine relation. If and only if we can find an element U in this W lower J such that, well, we have this actually V and W. But here in the middle, we have to multiply V prime and W prime by multiplying the U at the same time. I would say that actually in a case, if the J is empty, which is the full flag case, then this U must be 1, and then this is just there's no U here. So then this is just the V less than V prime less than W prime less than W. Then this is actually exactly the Chlorine relation which we described here. However, in the general case, because of the existence of such U, and this actually makes this partial order much more complicated. And well, so I would say that actually, in fact, this actually gives you a really challenging problem and to understand the partial flag varieties. And so the trick we're going to use is that we are going to actually to construct a nice atlas map. Well, so what do we mean the atlas map is that we're going to actually which actually provides locally a model of this the partial flag variety with the Schubert varieties in the full flag variety of a larger Kac-Moody group. And here the important part is that we want this actually as the stratified space. So which means actually on this actually PJ, we actually have this decomposition into the projective wishes varieties, which actually the Chlorine relation are complicated, and the geometrically how they are growing together, they actually are even more complicated. However, if you actually use this actually atlas map, what we expect that on the other side, I mean, the cost we have to pay is that we have to consider a much larger Kac-Moody group. However, what we gain is that what we look at is that we look at this Schubert variety, and the decomposition is that the Schubert variety is decomposed as disjoint unions of the open Wishens variety in the full flag. So in some case, in some sense, that we make this actually Kac-Moody group to be larger and more complicated to understand. However, that in the beginning, and the partial order and the green actually are in a very twisted way. And however, we have to use this the local model. Then in this the larger Kac-Moody, and we consider full flag, and then the Chlorine relation and how these cells are grouped together actually is actually in some sense they are more flat. Well, we understand this atlas map, which actually has the nice combinatorial and geometrical properties. And well, I would say that we also expect that they also has a nice positivity properties, but this is actually still in progress. And actually, let me actually mention one example. So in the full flag case, well, previously we discussed that we do have this decomposition of this open part, U axon B minus dot B plus. So we say that, okay, this actually is isomorphic to a Schubert cell times the opposite Schubert cell. However, if you look at this actually things together, then it's just a B plus times B minus orbit, axon U dot and U dot. So this one is actually is a Schubert cell of the flag of this larger Kac-Moody group G times G. And also the positive property which I mean here is that the same which we discussed earlier. And we'll have to say that actually for the partial flag, I mean, this is actually much more involved. And we still have the fourth statement and for this positivity, but actually we actually have some part of it which actually is enough for the purpose to prove the main result in the case where J is finite. Okay, so what are the atlas maps? And well, so this also actually has a long history, and so when G is a reductive group, And so this actually first actually this is the comes from an idea of the Anna Newson around 10 years ago. Then this actually joined with him and Jianghua Lu, and we came up with these actually definitions of the Buhua Atlas. Well, but however, I mean, this actually has never been published. So later actually, so in the last year, Galashin, Kaplan Line, and well, they actually defined a totally different one, which is called the Affine Atlas. And so, well, we start with the reductive group, but I mean, the larger Kac-Moody group they actually use is actually the loop group, or in other words, is actually the affine type. We actually need something actually which is totally new for arbitrary Kac-Moody. So this actually this is actually based on another joint work with Huan Chen, which is already actually on the archive, which we call this the Birkhoff, Buhua Atlas. So what actually this means is actually in some sense actually similar to the thing which you see here. This actually we actually do not actually use the Schubert cell or the opposite Schubert cell, but I mean you have to actually take some part to involve the positive, some part involves the negative. So this actually is the mixture of the Schubert with the opposite Schubert. So I mean the opposite decomposition into the opposite Schubert. Well, this is also actually called the Birkhoff decomposition. So I mean this actually the reason I will call this the Birkhoff Buhua Atlas. Well, since I'm almost running out of time, so I'm not actually going to give you the definition of this, but I would like to actually show you some examples from my joint paper with Huan Chen on the atlas. Is that we're going to see how, I mean, if you actually start with a partial flag, how do you actually construct this larger Kac-Moody group? So you can actually get some sense that how the things looks like. So here the most general case is that the first two columns. So we also actually compare this actually with some other constructions and with some earlier work. Okay, so in that paper we actually use a K instead of J. So here the K is actually the subset of the set of simple roots. And in this actually Dinkin diagram, we actually mark this actually with the black dots. And so what is actually the larger Kac-Moody? So the larger Kac-Moody has this actually Dinkin diagram. And so basically we actually look at these two copies of the I, but we are growing along K in a certain way. So here the vertices, they have the three types. Well, so for those actually, sorry, this the typos. It would be K. So for those lies in I but not in K, well, we have two copies. We use this is a white upper triangle and a white lower triangle. And in the middle, we actually grew together along the K's. Then we actually mix this upper triangle and lower triangle together, and so we actually get this actually the black diamond. Okay, so I would say that actually after putting all these things together using the canonical basis, and also this is a generalized Poincare conjecture, and also this atlas maps, and also some of the positivity structures, and then this actually we actually come to this main theorem. And this main theorem. Okay, I'll stop here. Thank you.
Thank you very much. Are there any questions or comments?
So can you just recap, please, where
Yes.
theory of canonical basis was used here in the...
Okay, so so in fact, we actually used it in the very beginning. And so, well, I mean, we have this is a totally positive part, and so then what we're going to do is that we use this March-rich parameterization. So then we are going to actually calculate this generalized minor. I mean, we want to show that whether or not it is actually contained in this like in this open part. This actually equivalent to say that we look at certain coefficient. We want to say this is non-zero. And so we actually using the canonical basis, and then we know that this coefficient is the so-called the admissible function, which actually the function which actually depends on the parameters on the left-hand side, but actually only involves the plus, multiplication, and division. And then this actually just means that either this is actually non-zero for all the elements, or it is constantly zero. But it's constantly zero, which means that this actually lies in the boundary, and then this we can actually lead to the contradiction.
Thank you.
So this is actually roughly how this actually is used. I mean, so without this, I mean, we actually don't have these decompositions. So this actually certainly, so this actually certainly fails if you drop the total positivity. And this actually we use the canonical basis in an essential way.
Thanks.
Oh, yes, I have a question also.
Yes.
Oh, so question is any hope to do something for non-minimal groups, like analogous to what Lam and Piliavsky did for GLM?
Well, so this question is not related to the flag variety, because actually for the flag variety, if you think about the minimum or the maximum Casimudi group, you actually get the same flag variety.
Okay, but the group for the group.
For the group, this actually this is much more involved. I mean, the most difficult actual part is actually for those imaginary roots, and I haven't thought much about that. So actually, I do not know how this can be generalized to arbitrary Casimudi. I mean, this is a really difficult problem, I think.
Are there other questions? Okay, so let's thank Xuhua again for this beautiful talk.
Thank you.